There we go. Hello, everybody. Nice to see you. We're at the start of week 11. So um, it feels good because we're getting marching right along toward the end of the semester. So, yeah, and hopefully you guys are in a good rhythm in this class. We do have a project out there, so I might should go have a peek at it today and get you thinking about planning in your time to work on that project. It's still has some techniques for the second project that we haven't talked about yet, but we're getting pretty close to where you'll have most, if not all, of the tools needed to do that project here in the next week or two. Okay, so yeah, apologies in advance. I'm probably going to draw pictures today, and so you're going to see my messy pencil on or pen on paper drawings, but like I've said before, it's just the way that I feel most comfortable doing it, and I feel like if I can get some flow about it when I'm drawing pictures, then I'm probably delivering the information in the best way that I am able to do it. Um, Obviously, there are people who can use the graphics pads who might do a cleaner presentation than me, but I tried the graphics pad and I just didn't like it. Okay. So a couple of things from week 10, and I'm actually going to draw pictures of this just to make this go a little bit faster, just to close out the idea. So I do think that it is useful to keep it in your toolkit that you can use bitwise logic to manage large amounts of information in a very small amount of space. You've all done true false kinds of stuff in your programming at this point. I just had this moment where I thought I wasn't having audio, but it's okay. Um, yeah, so you've all done true false kinds of things, and it turns out that there are plenty of software systems where we are keeping track of some number, possibly many, kind of true false flags or switches, and bitwise and or are convenient ways and efficient ways to manage that. So let me just bring up the picture real quick and talk about, most of you got this, but for those of you who struggled with it, the using and to clear. So if you need to clear out a set of bits, you can use and, but then you also need to know what to do with and if you want to clear no bits. So I'm just going to do a whole bunch of examples here of clearing bits. So if I'm just going to work with one nibble, I'm going to go left to right. Clearing one nibble. To clear a nibble with you and it with zeros. And I'll just show you quickly that if you and anything with the zero, you get a zero out. So I just used and. You might think of this as a filtering value. So took this value, I filtered it with bitwise and through zeros, and I got zeros out. And that works for any combination. So it doesn't matter what the bits are in the incoming value. If you bitwise and them through a zero filter, you get zeros back out. Even if they are all ones, if you and all ones with all zeros, you get zeros back out. So that's how you use and to clear bits, is by anding some value through zeros for all of the bits you want to clear. And it doesn't matter if some of them are already clear or not, you still get zeros back out. Now, sort of the opposite holds true, by the way. So let's say that you want to preserve if you want to use and to preserve bits when you filter, then you use all ones, and if you use all ones, then wherever you started with a one, you get a one back out. And it doesn't matter if it's all zeros. If you, oops, the filter is ones. Doesn't matter if your start value is zeros and you preserve your start value through and bitwise and ones, you get the original value back out. The important one though is that you can preserve bits with bitwise and by using all ones. So the situation would look something like this. So when you're programming, you're probably familiar with this. I know you're familiar with this concept. When you are programming, you don't always know what the incoming data is. So here's two nibbles. I don't know what they are, but if I'm told to clear these and preserve these, I don't care what they are because I already know how to use and to do that. So if I'm supposed to preserve all of these in their current state, whether they be all ones or all zeros or some mix of ones and zeros, it doesn't matter. If I'm told preserve the bits in that nibble, then I'm going to AND them through ones. And if I'm told to clear all the bits of this nibble, it doesn't matter what they start as. I'm going to AND them through all zeros, and I will get whatever. I will get all zeros down here, and then these will be preserved. So that's kind of another look at AND. Of course, you could Google this and I'm sure find, a million different presentations, this exact same idea. But so bitwise AND is very useful for clearing bits. But you can also, while you're clearing some bits, you can preserve others with bitwise AND simply by choosing the right filtering value. So in this example, I am clearing the lower nibble and preserving the upper nibble by ANDing the original value through this filtering value, this ANDing value, which clears the lower nibble, and whatever the upper nibble was, it preserves it in its original state. Okay, so there's that one. And then the ORing one. So bitwise AND, you can clear stuff and you can preserve stuff. Bitwise OR, you can basically only set stuff. So the same kind of thing applies though. It doesn't matter what I start with. If I am told that I have a start value and I'm supposed to turn on this specific bit, then I will OR it through this. To get this. These values remain as they were. It doesn't matter what they were. If you OR a 1 with the 0, you get the 1 back. If you OR a 0 with a 0, you get the 0 that you started with. So you can use OR to turn on specific bits in the sequence. And then if you leave the filtering value at zeros, then you get preserved what you started with. So this ORing value simply turns on this 2 to the first bit, and it leaves untouched the other bits. They are preserved in whatever state they were to begin with. So if you were to use bitwise logic to store Boolean flags, you would use OR to set things true. And then you would use AND. You could use AND to both check to see what is set to be true, but also you could use AND to turn things back to be false. Because if you AND something with 0, you get a 0. And if you OR something with a 1, you get a 1. Okay, so just really quickly on those things, because there were enough people who just didn't have any value there. And I assumed it's because they didn't really know how to deal with that. Although no one ever asked in Piazza, Canvas Inbox, or office hours. No, that's not true. One person did come to office hours and asked, and we worked through it. But anyway, for those of you who didn't ask and didn't know, there's that explanation. I'm going to keep drawing while I am at it for the time being. Okay, switching. Or should I walk through the module first? Yeah, I think I'll do that first. Let me switch back over and walk through the week's module, see where we're at. Zoom in a little bit. Okay, so we are in week 11. We are doing addressing modes. Addressing modes is, you've used them before, and the discussion, which one of the sections has already started, will explore where you see addressing modes in high-level programming languages. But the way that you access data in a processor architecture is one of the things that can most set one architecture apart from another. So processors allow different levels and mechanisms for accessing memory. And because we're in x86 class, we'll look at the way that we access memory in x86. We've already been accessing memory, by the way, all semester long. We have been creating static variables, which are stored in RAM and accessed through the variable name. That's called direct addressing, by the way. And we've also been using the registers to hold data as we perform calculations and the like, or to use them as middlemen for comparisons. So we've also been using the registers more or less as an additional set of readily available variables for storing data. And we've been using direct addressing mode with the registers as well. So the way we've used registers up to today, we call direct addressing, because that means that if I want the data, I go directly to the register and there is the data. Or if I want the data and I have a variable for it, I go to the variable directly and that's the data. So that's one addressing mode, is called direct addressing, or the fancy term for it is displacement only addressing, which is not super meaningful to me. Okay, Project Tues out there, by the way, due December 11th. Let's pop it out open and just see what we know how to do so far. So the second project is about, in no small part, using the addressing modes in x86. So today we start getting those tools. Dynamic memory is coming up soon. We don't have that tool yet. We do know how to use the stack. Not everyone has been practicing with it, but I recommend that you take opportunities to use the stack. x86 arithmetic, although we will need to switch over and start doing signed arithmetic, which we will do soon. But anyway, after today, you have 3/4 of these things at least introduced to you and practiced through labs. All right, so what do we do on the project? This is looking down the road, but just so you can start making a shopping list. Create a dynamic array of int 8s. Okay, we don't know how to do that yet. So that one, somewhere up the road, we will encounter that. A little user input, we can do that part. Creating a variable to track some data, we can do that. So let's see, number 1, we can certainly do that. Number 2, we can't do that part yet. So we haven't done arrays, so not number 3. So there's a lot that we can't sort of directly do, but anyway, I just want you to be aware that the second project is out there, and you should start gathering your intel about how you're going to do that project. Sums, averages, minimum and maximum values. We've done miniaturized versions of those, but not with arrays. So once we get arrays in our toolkit, then even if they're not dynamic ones, we can start to build out parts of the second project. So just keep it in mind that that is your ability to solve large parts of the second project is coming very, very soon. So you want to be aware of what the project is, so you know where you can apply what you're learning and practicing in the labs. Yeah, so that's that. All right. Anyway, just so you don't lose track of it, it is due on December 11th, which is the Sunday before the last week of class. All right, week 11. Maybe. Okay. Okay, so addressing modes. The concept of addressing modes is simply how do we access data. It turns out there are different ways of doing this. If you have used a pointer in a programming language, then you have used a different addressing mode from the direct addressing mode, because an integer variable and a pointer to an integer are two different ways of addressing, which is a way of accessing the data. We will look specifically at the different addressing modes that the x86 processor allows. There are 4 of them, more or less, and we'll do 2 today. And then we'll look at the HLA side of things. So how do you practice this knowledge with the HLA language? So we will get addresses of things and in 2 different ways in HLA. So there's an address of operator, and there is an assembly instruction that gets addresses of things. And then direct to register, direct to variable, and then indirect, which is by address. Okay, that's goals. Couple of readings, as always. Homework like normal. The lab, let me pop open the code part, and then I will come back to that and give us some tips before we close out for the day. I put an exclamation point. I wonder if I always do that. So one of the classes has already started this discussion, but you will discover actually that many high-level programming languages have syntax that allows you to make use of processor addressing modes. And one of the more obvious one for many of you, either now or in the very near future, will be C++ pointers, which is an indirect addressing technique. And then the reminder, so homework lab discussion as always, and then please start peeking at the second project on a somewhat regular basis so you can decide at some point very soon you're going to see in a lab something that you can use on the project if you are aware of what the project is asking. So that's how you can do yourself a favor. All right, so I think I'm going to switch over and draw some pictures to try to explain before we look at it in code what this addressing stuff means. So let me switch over to my paper. Okay, so you are accustomed to direct addressing because it looks like this. I'm just going to do one example. So let's say we have a static int 8 that we have declared in an HLA program. So what does it look like in code when we are using direct addressing? When I say the variable, the label basically, the identifier of the variable is the data. It looks like this kind of thing. This is direct addressing. When we say move the value 10 to X, we are saying move the value 10 to the memory location that X represents directly. That's direct addressing. X means the data. X, after this move instruction, wherever X is in RAM, we don't know, although we could get it. Wherever that is, it doesn't matter. It represents the piece of data that's associated with it. This is the kind of addressing that we're all very, very, very used to and comfortable with. Variables mean the data. I mean move 10 to that variable location. Yeah, so Druid Dread asks, what if I put the X in square brackets? In assembly, that means we're not doing direct addressing. So I'm going to come back to that in just a second, Druid, about what the square brackets would mean. So in x86 assembly, if you see an identifier, that's direct addressing. That just means that X is the X. It's the data. Here's another one. Direct addressing. What I want to output is the data that the label X is associated with. So direct addressing is the one that you are used to. You look at an X in code and you say, that is the data. I want to overwrite that data with some new data, or I want to print whatever the current value of that data is. Same thing here. Direct addressing. I mean whatever X value is. Directly, whatever X value is. Here's AL, by the way, and AL is being used directly as well. So we can also do registers directly. So here I am using AL just like any other variable. Remember, I mean, more or less the registers are kind of built-in variables. They're just heavily used and reused variables. So we have to be careful with them because they get overwritten a lot. But I am using the register directly for the data that I want to associate with it. I'm copying the value 1 into AL. And if I print it out, I want the data. Now we know that hex is going to be used to present the data to us, but it doesn't matter. It's still, in this case, I'm using the register more or less directly as the data that is associated with it, which in this case is the value 1. It doesn't change if I do typecasting. I'm still just using the register more or less as another variable that is holding the data that I am directly interested in. AL is the data. AL is the data. AL is the data. Same here. X is the data. X is the data. X, in this case, both X and AL are the data. That's direct addressing, and it's the one that we've been using all semester without fail. It's the only kind of addressing we've been using, and it's most of what addressing you use in high-level programming as well. All right, so now let's do indirect. And then I have one more picture after this. So I want you to sort of keep your eyes open in code, which is why I'm kind of drawing it, but also I didn't want to switch the views around over and over and over again. Indirect addressing. So, and then I'll draw a picture kind of conceptually of what's going on in the computer's RAM. So indirect addressing means that we are getting at data indirectly. That's all it means. We do this all, I mean, I guess you do it with your computer, you do it with Google Maps, but if you have handled a phone book in your life, that's helpful. Or a map, say of Butte College. If you've ever handled a phone book, you open the phone book and you look up Boyd Trollinger in a phone book, you get my address. That's not me. That's a way to get to me indirectly. So indirect addressing is I go to the phone book, I get an address of the thing, and then I have to travel to it to get Boyd, who is at that address. That's the way conceptually I deal with this. So indirect addressing means that I don't have the data, but I have a way to get to it indirectly. Now in code, this looks quite a bit different, unfortunately. But let's just look at what it looks like in code before we actually set it up properly in code. So we will have, well, let's just start with registers. So if you see this, and this is what Druid was asking about, if you see square brackets in an HLA program, i.e. an x86 assembly, that's indirect addressing. It just is. There are two kind of more elaborate means of doing indirect addressing, but basically that's indirect addressing. So you don't even have to think about it. If you see square brackets in HLA, that's indirect addressing. It just is. Um, so what these brackets mean, though, is that EAX is not where we want the data to go. EAX is actually a reference to some other location where we want the data to go. So the square brackets say, take the address and go there. So take this 0, not put it in EAX, but rather go to wherever this address is and dump the data there indirectly. So EAX is not the data, it is the address of the data, which means that I have to square brackets, travel to the location where the data actually lives to work with it. It'd be the same kind of thing if we do this. We might say type int 8 EAX. So if I see the square brackets, indirect addressing, guaranteed. There's no other way to make these square brackets mean anything in HLA or in x86 assembly that is not indirect addressing. It just is. This is indirect addressing, period. There are a couple of specialty types of indirect addressing, but they use the square brackets and they are still just variations on indirect addressing. So what does this mean again? This means I don't care. I don't really want what's in EAX. That's not the data. EAX is referring to some place where the data is. So I use the square brackets to dereference, is the C++ term for this, to not use EAX for the data, but use EAX to travel to a memory location, get the data, and then typecast that data from that location for the purpose of printing. So Druid is asking, what's the difference between moving 0 to EAX? Then I am using EAX to store the actual piece of data that I want. So if I take the square brackets off, I'm saying put the value 0 in EAX. Now, I haven't talked about how do we get the addresses of things in EAX, but what precedes the square brackets is an address has to be in EAX, which we'll look at in code. So, but the first thing is just some eye training, which is square brackets, indirect addressing. Square brackets, indirect addressing. But if you see EAX without square brackets, that means don't do this. Don't travel anywhere. EAX has the actual data in it that I want. If you see the square brackets, then you're saying EAX is not the data that I want. I have to actually use EAX, square brackets, travel to the location of the data to get the data for the purposes of this output. Same here, just kind of in a copy. So take the value 0, put in EAX? No. Take the value 0, travel to wherever EAX is referring to and put the value there. So Druid asks, doesn't EAX have an address? Not really. EAX doesn't really have an address. EAX is EAX, is EAX. It doesn't have an address. It just is a thing that is always present. It's like an ever-present variable. But it's a multi-purpose variable that can be used for different kinds of data, although not different amounts of data. So EAX does not have an address. It just is on an x86 processor. You could say that the label EAX kind of is the address, but I wouldn't think about it that way. EAX just is an ever-present variable in x86 assembly. And it is a multi-purpose variable. It can be used to store data directly, or it can be used to store addresses that allow us to get to data indirectly. So these are good questions, though, so keep asking those kinds of questions. Okay, so before we look at sort of the conceptual view of the memory itself, why am I using EAX here? More particularly, why am I using it here with the square brackets? So all addresses in our class are 32 bits. So whenever we are doing anything indirectly, it will always be 32 bits because the thing inside of the square brackets is actually the address of something else. So all addresses are 32 bits. That means that you will always see 32-bit something in the square brackets. In fact, for us, it's always a register. 32 bits. So indirect accesses are always through 32-bit locators, or addresses is technically the word we should use. So square brackets means that I'm going to an address. Square brackets means I'm going to an address. And the addresses are always 32 bits. So this EAX represents a 32-bit address. This takes some getting used to. So I'm just going to write down a big long note, which I could have typed, but I'm on the paper. So even if the data is not 32 bits, its address is. But that's also not dissimilar from the places where we live. So my address is my address, but so is the address of my coffee cup, my same address, even though I consume a lot more space than my coffee cup does. If someone wanted to locate my coffee cup with the street address, it would be the same address where they would find me. Now that's just for some of us to work our brains around the problem. Even if the data is not 32 bits, the address is. It just is. So in x86 32-bit assembly, the address of everything is 32 bits. The address of 8-bit variables is 32 bits. The address of 16-bit variables is 32 bits. The address of 32-bit variables is 32 bits. So these square brackets that take you to a location where data is being stored are always 32-bit locations, but the data that you find there may not be 32 bits. This is kind of, I think, some of the mental gymnastics that are healthy about this class, is just to think about from a computer science perspective, the how computers deal with data, and how we then, as people on the software side, deal with data as well. Okay, so that's a big long mess. Every address we ever have in this class will be 32 bits, no matter what it's the address of. They're always 32 bits, which means that everything that you see inside of square brackets is going to be 32 bits, at least today. We will get some variations on indirect addressing, and we will toy around with what goes in the square brackets a little bit. But for today, it is suitable to remind yourself that everything in the square brackets will be 32 bits, because what's in the square brackets is always an address. Okay, so one more picture before I switch. Before I switch to text editor on the virtual machine. So what is all this addressing stuff? It's RAM. So we are talking about the computer's RAM. Now we might also think to ourselves, if we're in the CPU that we have built in, I'm just going to draw a subset of them. And then the CPU and the RAM kind of, the CPU can go fetch data from RAM. So one thing to keep in mind is that when we talk about the registers, those are memory banks hardwired to the CPU, and they're just more or less always available, always present variables that we can use. It's one of the nice things about them is that they are high performance because they are already built into the processor itself, and they require no work to go out to RAM to fetch any data. They just are present and can be used for data or addresses, as it turns out. They're very, very, very flexible. Okay, so in RAM, it turns out that we conceptualize our use of RAM as two kind of sections of RAM, even though technically that's not physically what's happening. But conceptually, we separate RAM into kind of the program stack or static memory, and then heap memory, or the free store. The terms don't really matter just a whole lot. So we have conceptually anyway, we use the computer's RAM in two different ways when we program. So as programmers, so far we've only ever used static memory in this class, but we often, that's not even legible. Heap memory, or some people like to call it the free store. Okay, so static memory, heap memory, but it's all still RAM. This isn't two separate units of RAM. This is just the way that we kind of conceptually use our memory resources as programmers. So the static memory is used whenever we declare a variable. So you might think of this as just kind of some number of memory cells in our variables are associated by labels with memory cells in the static memory part of our RAM use. Hopefully that makes sense. When we declare a variable, we are grabbing RAM for our program's use. And the RAM that is associated with our variable declarations is accessible directly by the variable identifier. In other words, if I write X in my code, I mean the data that's here in this memory cell. If I write Y in 8, let's say, then I use the label Y to get to that memory cell where the data is directly. But we have this other area, which we're not using this week, but we will next week, called the heap. And I'm just drawing a picture that kind of looks like a heap. The static memory that we use is highly ordered, and we'll look at that when we write up a little test program. So when the compiler builds our code, it sets up all of our variable declarations, the memory for them, in a highly ordered fashion. What we're going to end up doing before the semester is out, though, is we're going to use dynamic memory allocations. So we won't declare all of the variables that we need. We will allocate some of the memory we use as the program is actually running. That's dynamic memory, which we're not doing this week, but I think it can help to consider when you're learning about addressing this concept. So static memory, when we declare a variable in our code, we are using static memory, which is we are using RAM locations that are set aside and labeled for our use. Static memory is very easy to use because we just use the name of the variable to get to that memory cell which contains the data of interest. The free store has no labels associated with it. So one of the reasons why I'm showing you this picture today, even though we're not actually doing heap memory this week, is so that you kind of maybe can develop the picture in your head that the heap is unlabeled memory. It's completely unlabeled. But that's not to say that it doesn't have addresses in it. So every cell in RAM has addresses. I'm just going to lazily label them cell 1, cell 2, cell 3. And then maybe these are like cell 10, cell 11, 12, and so on. So I know you can't really read this, but these numbers don't matter. All I'm pointing out to you is that there is a hardware address associated with our variables, um, and we will print those today. But when we declare a static variable, we no longer have to worry ourselves with the hardware address of that cell in RAM because the variable label itself takes us there. So this is a huge convenience for programmers that we just take for granted that I declare a variable and that variable represents data. The reality is that label is a gift to us because that label gives us a shortcut, a very convenient way of going to a specific hardware location in memory with its own hardware address and getting data. That's great about static memory. Variable name equals memory cell at a specific hardware location. The problem with the heap is that we can't put variable labels on the heap. That's not how that will work. So the trick to using the heap is that we will have to use the addresses to get to the data. And in fact, we're going to do that on the stack as well, but I think it's next week. Maybe next week, maybe the week after, we will use the heap. So I wanted you to see this picture that the static memory part of RAM, we have convenient variables labeling the memory cells we're using. The dynamic part of RAM, the heap, we don't have variable labels. We have to use the addresses to get to things. If you have written a pointer in a programming language, that's what the pointer was actually doing, is allowing you to gain access to this memory that is unlabeled by your variables but addressable. That's what pointers do, is allow us to actually get to these addresses in the free store. And then don't forget that the registers kind of just are magically constantly present. All right, so now I'm going to ruin this picture before we go look at actual code for a second. So here's something that kind of freaky that can happen. We have a fair amount of power to store data and addresses anywhere where data and addresses fit. So let me deal with a question in chat. So I thought pointers referred to the variable address, which should be in the program stack. They can. So the question is, don't pointers just refer to the static memory? And the answer is they can, but that's usually not how they're used. So pointers can be used to point to locations because we're really just talking about memory cells organized for different purposes. But pointers are typically used to reference memory cells in the heap that are otherwise unlabeled. That's their typical use. But we have a fair amount of freedom, especially at the assembly level. We have a fair amount of freedom at the assembly level to store different kinds of information in different places, which can make it very difficult to track mentally. So we can, for example, store, and I'm just going to draw arrows here. We can actually store heap memory addresses in registers and then use the address that's stored in a register to get to the heap. This arrow, by the way, looks like this in HLA or x86 assembly code. That's what this arrow means. Is EAX is actually referring to an otherwise unlabeled, in this case anyway, but addressable cell in the computer's RAM. That's what I've drawn here. Now here's something weird. I can also do this. I can actually also store the address of anything, not just heap memory, but also stack memory, because ultimately this whole thing is just memory cells that are organized for convenient, less convenient uses. Static use, dynamic use. So I can actually get the address of something in my static memory and put that in a register. The code for that looks like this. So there's EBX, but not EBX, but what that address refers to, which is here. So in this case, what I've drawn is really what we can say about my little picture here is that if I dereference EBX, that's the same thing as just going straight to X. Now, it's impractical that I would do this other than for learning purposes. If I already have a label on memory, why would I then store the address to that memory separately and then have to dereference it to get it? I just want you to kind of see this, that in this case, if I go to EBX, knowing it's an address, and I dereference it, I get the same data as if I went straight to X, which is the convenient variable label on that same cell in memory. So that's all variables are really, is just super handy labels to memory cells that don't require any extra work. You just say X and you get the data. But we won't always have that convenience. Sometimes we're only going to have the address of the data and we're going to have to dereference it to get to the data itself. All right, one more, and this one's kind of weird because I can actually also in static memory store the address to things. So I can actually store an address to heap memory in my static memory. The code for this would kind of look like this. Unfortunately, if you store an address on the static memory, you can't use it from there. So you actually have to copy that address from static memory into a register. So now I have copied, so now I have two references to that same cell in memory, one in this address variable and another now that I've copied it into ECX. And the reason I did that is because this is the only way to actually use the address. So this is kind of weird, isn't it? I'm storing the address in a variable, but I can't use the address from the variable until I have put it in a register. Now I can use the address to get to the cell. Why I would do that is hopefully a question you're asking, like why would I then even trouble myself with this extra step of storing an address in my static memory, knowing that it's going to have to be placed into a register before I could use it anyway. And the answer is because these are constantly being written and rewritten and overwritten, and they're very, very, very volatile. So sometimes we are going to store addresses in our static memory so that they don't get lost. Because if we lose that address somehow, then we lose the data. Yes, so that one kid is asking, is this the same thing as when we do pointers in C++? And the answer is yes, it is. In fact, I'll do a demo, do a short C++ demo just so you can see what this looks like in C++ syntax. Yes, so an address can have an address. That's correct. Yeah, it's a little bit mind-blowing. Yes, UG is true. So yes, you can actually store an address to a thing, and then when you dereference it, it is yet another address that takes you somewhere else. So file systems on computers do this kind of thing all the time. And in fact, in programming algorithms too, we do a fair amount of addresses of things. In C++ parlance, we would say a pointer to a pointer. Yeah. It's almost like, what do you call those things? Where they give you a list of like random things to go grab, and every time you go get the random thing, they send you somewhere else. Something hunt. What's that thing? Scavenger hunt. Thank you, Druid. It's like a scavenger hunt sometimes in code. Because I'm given an address, I go to the address and I discover, oh, this isn't what you want. You need to go to this other place. That is very, very true, and it is very difficult to track in code, and it is the source of lots of programming errors. It is hardest in assembly. It's easily most difficult in assembly, but it is pretty difficult in high-level programming as well. There are languages that have tried to eliminate some of this pointer-to-pointer-to-pointer stuff. Python pretty much has eliminated the problem. There's trade-offs there because you lose some efficiency. Java has mostly kind of eliminated the pointer syntax, but C++ certainly has not. Okay, so one thing to note here before we leave this page and go look at actual code, square brackets, indirect addressing, indirect addressing, indirect addressing. This X, direct addressing. This move instruction, direct addressing. There's no square brackets, which means that it is by definition direct addressing. Even though we know that the information being copied around is ultimately an address, but we're using the direct addressing mode. So square brackets, indirect addressing mode on x86. No square brackets, direct addressing mode on x86. It is kind of cool though when it comes together in one's head. You feel relief, maybe, some sense of kind of accomplishment that I got this piece of information straight in my head. So yeah, one thing that I'm pretty sure the picture does show is that this can be a complicated mess, and it most definitely can be. Now let's look at a piece of code, and then I will kind of walk us through. Okay, gotcha. We'll look at some information in code. Let's see. Oh no, I just show. This is week 11. All right, so let me make sure you see what I see. You do. So what does it look like in code? Having bad typing finger day. So let's do a couple of static variables later. Let's make an X, which will be an int 8. And then we will do an address, which will be a D word. Okay, so these are both static memory uses. Int 8, everyone knows what that is. It's a signed 8-bit integer, and that X will be the label to the static memory portion of RAM that I'm using. And X will allow me to directly access the data at that static memory location. But it does have an address, so let's look at the address of the thing. So I'll just remind you of this constantly. So I'm using HLA syntax to get the address of X. So not the data of X, but what is its actual, what's the address of the memory cell that X is associated with? This is the same syntax that we use in C++ and in Go, right? I think so. So the address of X, not the data itself, but the address of it. Copy that address into EAX. So the reason why we're doing this is because we must copy addresses into registers to use them. And then I'm reminding you that even though X is 8 bits, its address is 32 bits because everybody's address is 32 bits in 32-bit x86 assembly. The reason why we did that is because we can now say Address of X is $sign. And we'll just look at literally just the raw hex data for the address of X. Not X, the address of it. So that address is just wherever the operating system happens to put my program's memory into. So that is the hardware address in RAM of my variable X. So X is associated with that specific hardware address in RAM. Right, so that question again, so I'll show you what happens. So if we try to move the address of EAX into something, we should get a compiler error. So registers don't have addresses. They just don't. They are just built in. EAX means the memory cell on the processor, and there's no other way to refer to it. So yeah, that doesn't work because EAX doesn't have an address. EAX is the label of that specific memory cell on the processor, and that is the only way to reference it, is with the label EAX. So even if you tried to get the address of EAX, you can't because it's meaningless to do so. The registers are just a little bit different than regular variables because they don't live in RAM where every cell has a memory address. They live on the processor where they have predetermined labels. Yes, the picture I drew did link ECX to a heap address. That's true. But I can link any register to a heap address. That's true. So I have linked actually this line 12. I have linked EAX to the same cell of memory where X lives. And I'm going to print out X first. So I have not used indirect addressing yet in this program, by the way. There's no square brackets, meaning there's no indirect addressing. There is address information being referenced, but I'm not using the address mode itself for accessing data. So here's X. Let's put some data in it just so we can see the 99. This is direct addressing mode, and then we will do X indirect. Let me line these up. I feel like I made a typo. I don't think so. Okay, so hopefully this helps a little bit. So I am copying the address. X is a convenient label that my software is associated with a RAM memory cell. So I've taken that actual address, the hardware address of that memory cell in RAM, and I've copied it into the register EAX. And then I print out that address value. So EAX on line 13 is the hardware address of the memory cell that the label X is referencing. Line 15, I'm using direct addressing to see the data at X. So remember, static variables in HLA, and in fact most variables in your programming, are simply convenient labels that allow you to work with memory cells without the inconvenience of indirect addressing mode. So the language is kind of giving me this feature where I can just say X and that's the data. But I could, if I wanted to, and I'm going to in this case, actually use the address EAX, which is the same hardware address where X is labeled, that X label refers to, dereference it, meaning go out to that memory cell, interpret the data I find there as int 8 and print it out. It's the same data. So I don't know if that caught anyone off guard or if everyone just thought, yeah, that's what we expected to see. But if X refers to a memory cell directly, and EAX as the address of that memory cell refers to it indirectly, and I dereference that indirect thing, if I dereference its address, I get the same data at the same cell. So X is a super easy way to get to that memory cell. Dereferenced EAX is the indirect way of getting to that exact same memory cell. Yeah, so there's that. I can also do this. Let's make it a, I don't know, 33 instead. So I can also access that memory cell and overwrite it. So again, EAX is not the cell, it is the address to it. So I dereference it, which goes to the cell, and then I can deposit this value 33 at this location in RAM. And if I do that, and then I go look at what X is, well, X is the same memory cell as that indirect reference that EAX is currently holding. So X is accessing the same cell directly that I was using the address in EAX to access indirectly. Yeah, so Druid asks in chat if the analogy of X is the front door to the data and EAX is the back door to the data. Would that be appropriate? That makes sense to me. I think you can use that way of explaining it. X is the direct, i.e. the front door to the data. And if we load up its address somewhere, then we can use EAX as the indirect or back door to that same data. So that makes sense to me. I think you can absolutely use that analogy to explain it. Except for I made a mistake somewhere. Line 18. Oh, yeah. So sometimes you're going to get weird errors like this. The problem with this move is that the HLA compiler doesn't know how much memory to use. So you sometimes have to, on both ends, say, actually just fill 8 bits worth. So I got a compiler error. It looks like this. Unexpected square brackets. It's not super helpful, but I know from practicing in HLA that the compiler is really telling me, yeah, this is an address of a cell, but how big of a cell are we talking about? Is it a 32-bit cell, a 16-bit cell, an 8-bit cell? So I'm going to go ahead and tell HLA, yeah, it's an 8-bit cell. So this address is for an 8-bit thing, and that will help HLA figure out how much to fill. So sometimes you have to use the typecasting trick so that HLA knows how big the cell is that you're talking about. How did I know it was an int 8? I had to remember that. And that's actually the whole answer to that question. How do I know I should type to int 8 here? I know because I can sort of backtrack my way. So EAX, oh yeah, if I'm dereferencing EAX, what is that? Well, oh yeah, it is, currently it's the address, and I like the backdoor analogy, it's the address of X, and X is an int 8. Okay, so if I'm going to deposit data in that memory cell that EAX is the address of, I need to make sure that HLA knows to only use 8 bits there. This is a pain in the rear. But anyway, there is some direct and indirect kinds of things. Okay, so now let's use the dword address. So dword is an appropriate data type for storing 32-bit addresses because dword is a 32-bit sort of untyped piece of information, which is a good way to explain what an address is. an address isn't an integer, and it's not a string, and it's not a char. It's just hardware address information. So dwords are appropriate for that, and I am going to use the label address. So this is static memory, and I'm going to actually put an address in static memory. Now this is kind of an artificial example, I know, but the reason why we create static variables for storing addresses sometimes is because we know that we're going to need the address for a long time through the program's run, and we don't want to risk storing the address in a register and forgetting to not overwrite the register, and then suddenly we lose access to the memory cell that the address was referring to. So we use these static variables for long-term storage of hardware addresses when we have any doubt that we might forget and lose that address. So losing an address of something is bad when we start doing dynamic memory, because that's a memory leak. Okay, so now this variable address that's static memory, but I'm using it to store the address of something else in static memory, which is artificial. We would rarely actually do this, but just so you can see the syntax of it, I'm moving the address of x into a variable. Now I know I still have x to get to it, so that doesn't matter, but let's leave x behind for a while. But we'll go ahead and print the address here, just so we can prove that we can actually store the addresses of RAM memory locations in variables, right? And you'll notice it's the same address because x didn't move, but I just am storing the address in yet another place. Okay, so why would we do that? Well, mostly so I can show you the syntax. So can we do something like this then? Okay, so this again, I'm doing it so that you have been exposed to the complications of doing memory management stuff. So this is all about memory management. So how do we use memory? Well, the easiest way is to create variables, but we have other techniques for using and managing memories. We can store addresses, we can dereference addresses. We can actually, starting pretty soon, allocate memory dynamically. So we can actually get memory into our running program without having to label it as variables, which gives us a fair amount of power to create adaptable software. We'll get to that. Anyway, I want you to see some of the errors that you are going to see while we're at it. So can I go and dereference the address variable itself? The answer is no, unfortunately. So you can store addresses in static variables, but you can't use those static variables to get to the memory cell. You have to, unfortunately. I'll use B this time. What the heck? You have to have the address in a register to use it. So I can store addresses in static variables, but I can't use those addresses until I put them into a register. So yes, there is a lot of extra work associated with doing these memory tasks. I use DBX this time, which is 32 bits, so that's fine. Just to show you that we don't have to always use EAX. Any 32-bit register will do. And we get back ultimately through to that same data that X is. So we've just been sort of beaten away at that memory cell that X labels. We've taken its address and then used the address to get to it from EAX. We've taken its address and stored it in a different variable and then copied that address to a different register and used that address to get back to that original memory cell that X is labels. It's crazy stuff. It takes a lot of getting used to. I gotta stop and think for a moment because I've been talking just kind of dead on for a while. When we start using dynamic memory, then we will have, I want to get the syntax a little bit comfortable. You may not be fully comfortable with it for a while, but at least we'll begin to kind of work on the syntax. Know that when we see square brackets in our code, we are looking at something that's an address of something else, and we are going to whatever the address refers to. We want to get used to the way that looks before we introduce the additional complication of dynamic memory, where we actually allocate memory and then we only can use addresses to access it later, which is I find quite interesting, but we'll go slower steps. Okay, one last thing I think that we need. So if you see square brackets, that's indirect addressing. If you don't see square brackets, even though address data is involved, we are only using the direct addressing mode. So square brackets must be present for there to be indirect addressing. If there are no square brackets present, then we are using direct addressing, even if we know that somehow address data is involved. It's not the address data itself that really matters. It's when we use the address data to get to addresses, to actually go into memory. So no square brackets, direct. Square brackets, indirect. All right, one last operation, which we'll just use it today. Even though we don't have to have it, but then we will have to have it when we start doing dynamic memory. So this week is mostly about just getting comfortable with the syntax of indirect addressing mode. All right, so one last thing, which is the x86 instruction, LEA, which stands for load effective address. It is the address of instruction on x86. There is one huge problem with it. It is backwards. So load effective address is the other way in HLA to get addresses of things. Technically this week we don't need this instruction because the ampersand is all that we actually need. But there are situations where you cannot use the ampersand. And very soon, then that's another dynamic memory thing. So trying to get accustomed to the idea that we have two ways of getting the address data itself. We have the ampersand, the address of operator in HLA, which gets us the address of a static variable. And then we have load effective address, which is the x86 assembly for accomplishing the same kind of thing, which is get me the address of something. The main thing that is off-putting to me about load effective address is that it is backwards. So the thing you want the address of goes on the right, and where you want that address to be stored goes on the left. And it is, as far as I can remember, the only backwards instruction in all of HLA syntax. Yeah, it's a bummer. So anyway, load effective address of the where X refers to. Take that address and copy it into ECX, at which point then we can use ECX. So now we got this address to X all over the place in this program. Through, not through ECX. which we knew was going to be 30. So we have the address. We have ways of getting to that memory cell that X is labeling all over the place in this code. We have X itself, which is the easiest way to do it because that allows us to directly access it. We just use X and we get the data. We have on line 12 copied the address of that memory cell that X labels into EAX, and then we use EAX for indirect addressing purposes to get to that same memory cell. On line 21, we are copying that address that memory address that X is labeling into our variable ADDR, and then we are taking it on line 25 from our variable ADDR and putting it into a register. Why? Because addresses can be stored in static memory, but they can't be used from anywhere other than registers. So if I want to use the address, I need it in a register. So on line 25, I put it in EBX, and then I use EBX to indirect addressing to get to that same memory cell. And then the last one is I use the load effective address instruction to get the address of X and put it into ECX, and then I use ECX indirectly to get to that same memory cell. So EAX, EBX, ECX, X, and address all in this little tiny program have something to do with that one memory cell that X directly labels, which is cool and also very difficult to read. So one thing that you will all accomplish before we get to the end of the semester is that you'll be able to look at code like this and do the detective work to figure out what in the heck is going on. So if I see square brackets around a register, I know that that register has an address of something. The detective work is, what is it the address of? So if I start at line 16 and I just say, someone tells me interpret line 16 for me, well, I'll look at it and say, well, it's printing out some stuff. It's typecasting something into be an int 8, followed by a new line. So the something is the detective job. Okay, so this is square brackets indirect addressing, which means that that register is an address. So now I have to backtrack until I can find a reference to EAX. There's not one. Here's a reference to EAX, but that doesn't tell me how it got to have an address in it. And if I keep backtracking, eventually I see the address of operator. I'm like, there's how EAX got to be an address of something. I actually wrote an instruction that took the address of something and copied that address into EAX. Then I can sort of step back forward. All right, so EAX is the address of X. So when I'm dereferencing it, I am going to X. It won't always be that easy because we won't always be able to backtrack to a static variable like X. Sometimes our backtracking will find ourselves at a piece of code where we dynamically allocated memory that is otherwise unlabeled. And that will be a slightly more difficult detective job. Okay, I have a few minutes to do something in C++ that I'll try to do something similar to this just so we can see what it looks like. If that's okay with everybody. Oh, let's do, before I do that, let's get the lab code. So you're not gonna see me do it, but I'm gonna go grab the lab code, put it into the editor and see if there's anything tricky going on. Okay, so I'm seeing 3 static variables here, an 8-bit, a 16-bit, and a 32-bit. One thing I know for sure is that they all have 32-bit addresses. Doesn't matter if they are different size of data, their addresses are all 32 bits. Get int 8, that's been written for me. It's the robust version. Get int 16 needs to be implemented, but it's really just the get int 16 version of get int 8, so that should go pretty quick. Get int 32 is the int 32 version of get int 8, so that's mostly been written for me. I just have to make some adjustments with typecasting and some error output signals. Okay, so numbers 1 and 2 are just copy and paste get int 8 and make sure that it is correct for int 16, and then finally int 32. Go again's been done for me. Okay, so here's a couple more, number 3, number 4. So I'm going to talk through this code. So this function print value is receiving an address, although not in a register, unfortunately, an address in a variable, so I'm going to have to do something with that. And also a code, basically, telling me which type of data. The code telling me which type of data, we've done this before, but the whole problem is that we're going to have to do some typecasting somewhere probably, which means that we need to know what typecast to use. All right, so let's see how this has started. Copy the address into EAX. Why? Because if I'm to use this address, then it must be in a register. And I've even put a note there in the lab code. So this move has to happen because storing the address is fine and good, but we can't use it stored away like that. We need to copy it over to a register and then we can use it. Okay, so I type code 1. So notice what I'm doing here. I am dereferencing the address to get the data and copying it into BL. Now, why BL and not AL or BX or EBX? Because type 1 is an 8-bit thing. So I'm going to move to an 8-bit thing. I am being careful not to use AL because EAX is the address. So I need to use a different register for getting a copy of the data from that cell to a register and then printing it out. Why don't I use something like a variable here? Well, I don't know anything about that data other than what kind of data it is and its address and hardware. So I don't really have any options here. I have to dereference the address and I have to copy the data somewhere where I can conveniently print it without screwing up the address data itself. So I'll use B 8 bits worth. All right, so then what happens then? Although technically I could have done this. And that would have worked, but I want to exercise your brains a little bit with this move. So type 1 is 8 bits. So I go to that memory cell and I move 8 bits out of it. And then the output is simply doing the address value itself. Notice it's not dereferenced. So I don't want to see the data at the address. I want to see what the address actually looks like, the address value. And then I typecast BL, which has the data that I took from that address. So number 3 will be that same process, but with BX and int 16 typecasting. Type 3 is 32, so number 4 will be the same process, but with EBX. The address is going to be the same for all of them. It's the amount of data I pull. So number 4, the address is still EAX, but the typecast will be against EBX because I needed to grab 32 bits. Okay, number 5. Call int get int 16, call get int 32. Am I supposed to put that data somewhere? Oh yeah. Oh yeah, to get int 16, there it is. So anyway, number 5 is going to do the same process, but for the int 16 version. Number 6 is going to be the same process, but for the int 32 version. And then all I'm going to do from there is I'm going to prove that I can get the address of different sized variables and cause their addresses with the associated data to be printed out by sending them to a function. So same process 2 more times, except for the address of num16, the address of num32, and I'm going to be careful that I send the proper types with the address. So the 16 is a type 2, it's labeled. The 32 is a type 3. Is that the whole program? Nope. So then it wants me to I'll do this one. So, oh no, I already did it. Never mind. There's examples of all of them. So I gave you examples of the 8-bit version for all of them. Then you have to make the appropriate adjustments for the 16 and then the 32-bit versions of all of them. So there's actually nothing hard here. It's just convincing yourself that you understand what you're looking at is the trick. And it takes work and it is not easy. But you will get to where you understand it, and it will make you a much more powerful programmer in languages such as C++. When you deal with pointers, then you will know fully what those pointers mean to be saying. All right, I have 5 minutes. So anyway, make sure that you observe the code in the lab this week, because every section starts with an example of what is to come, the 8-bit version, and then you will do the 16, and then you will do the 32-bit. That's kind of 5, 6, 7, 8, 9, and 10 are all, you just model your code on the 8-bit version and make the appropriate adjustments. Same is true, by the way, for numbers 3 and 4. You model your code on the 8-bit section and make the appropriate adjustments. And then 1 and 2 are simply make adjustments to the get int 8 code for those. All right, real quick. I've only got 4 minutes now. C++ example of what these things look like. So I think I have time to do it without running you over time. So let me see if I can get it going real quick. Index equals 99. Stop bothering me with this stuff. So same kinds of things. I can have multiple things pointing at. And then so I have the static variable x. I have the pointer px1 that will be the address of x. And then I have the pointer px2, which is the same address as px1, which is also the address of x. So now I can get at x in all of those ways. One px1. Now my typing's really starting to fall apart. px2. So this is more or less that same program, but now in C++. Stop it. Same basic program, but now in C++, where I have direct memory usage and then indirect memory usage through pointers. The syntax is very similar in the Go language. I'll make sure it works, but... Oh, and I never showed the address itself. So we can also, turns out the C++, when you print a pointer out, will show you a pretty version of its hardware address. So that's the same basic program in C++. The syntax is actually not dramatically different from the HLA language. C++ uses the address of operator. The difference here is that C++ attempts to make it more obvious that you have an address of a thing with this star syntax. So int star px1 means pointer to integer px1. Px2 is also pointer to integer, which is an address. So that's meant to be more obvious when you see it in code than what you would see in an HLA program, which would just be a register or a dword variable. It's meant to be that when you do the detective work in a C++ program, you ultimately find px2 and px1 that say, we are addresses. We are pointers to integers. I'll try to keep this one around so that when I do dynamic memory, I'll have that as well. All right, it is exactly 2:30, which is when I try to stop. So I hope that I armed you with everything that you need to get through this week's work. This one is a pretty good thought piece. This address stuff is pretty weird, and the syntax and the resultant code are not the prettiest things to look at. So it does take some work and some concentration. Other than that, I'm available as always through all the channels. So Canvas Inbox, Piazza, office hours, so that if you have questions, I'm happy to answer them. And otherwise, have a great week, and I will see you on Tuesday afternoon next week. Thank you, Druid. Appreciate it. Have a great day, everybody, and I will hopefully see a bunch of you next week during the live stream, or in some way or another get to interact with you. So take care.